project.
All right. My name is Adam Dixon. I'm a Senior 2 Mechanical Engineering student at Kettering University, and I currently work at General Dynamics Land Systems.
My name is Matthew Vanderhoff. I'm currently a Senior 2 Mechanical Engineering student at Kettering University, and I work at Stellantis.
And this is the optimal aircraft wing design.
So when we knew that we could pick a topic of interest which related to fluid mechanics for the project moving forward, we decided to do one in the world of aerospace engineering. For both of us, we have a deep past with interests in this. For myself personally, I have multiple Air Force veterans in my family, and since a young age, I've actually been able to visit Air Force bases such as Selfridge Air Force Base in Macomb area and get to see actual, complex machines such as airplanes in real life. And that mixed with my interest in STEM and engineering has always made me inclined and inquire about aeronautics.
Yeah, and for me personally, the reason that I decided to go into engineering is just because I've always been fascinated with understanding how and why things work. And growing up, I always really enjoyed playing with paper airplanes and tweaking little aspects that would make it fly further or do spins. So this project really allowed us to combine kind of one of my biggest passions with something I'm very interested in. And so that's why we decided to pursue it.
Yeah, not only did this allow us to pursue one of our passions in aerospace engineering, but we also could apply that to the course content of fluid mechanics that we have learned all semester. So now to give an executive summary of the actual project in aerospace engineering we chose, we wanted to design two separate airfoils, which you can see here, in which we would change a design variable and test how that was changing the key fluid fundamental variables such as air density, velocity, and lift and drag coefficients along the foil.
Yep, so this experiment was achievable through designing using CAD, manufacturing with 3D printing, and then changing the aspect ratio of the airfoils in order to determine our variables and how they were affecting lift and drag.
And by changing various airfoil design variables, we also were able to see how it changed not only the key fluid fundamental items, but we could see what applications certain airfoils would be able to be used in real world. And now to go over some of the project goals. First, as Adam stated, 3D print, design, and modify different aeronautical wings and see how that is changing different variables.
And our goal with this project was to kind of confirm the validity of the theoretical relationships and applications that aeronautics have with force and lift and drag.
And by confirming some of those aeronautical theories, we would also be able to see the real-world applications in which different variables changed in a design for an airfoil would be able to be used for.
And our plan was to use the fluid fundamentals that we've been learning about the past 3 months to apply them to aeronautical and basically get the same understanding from that path.
So now to give some background information for fluid mechanics and how it relates to our project, an airfoil can be modeled as a solid body in an immersed fluid field. As it states as the first part of the word, the fluid that these are typically submerged in is air. And so the air submerged over them, due to the fluid no-stick boundary condition, there are going to be stationary fluid particles on the top and bottom surfaces of the foil. Also, there's going to be air moving with the velocity on the top and bottom of the airfoil, which creates a shear stress distribution around the entirety of the foil, as you can see here. Also, due to the various pressure and wind speeds over top and under the foil, there's also going to be a pressure distribution around the entirety of the foil. The combination of these two is what allows us to understand the fluid mechanics behind lift and drag forces. Another background information that is important moving forward is how density is affecting the airfoil and affecting our lift and drag forces. Density is directly proportional to our aeronautical forces such as lift and drag, meaning that if we are to decrease the air density, there is less mass of air around the foil for the wing to grab onto, meaning there's going to be less surrounding lift. Furthermore, inversely to this, if there is more dense or thicker air around the airfoil, then there is going to be higher lift and drag around it. And lastly, one of the key concepts behind aeronautical wing design that is crucial to our project, we knew we wanted to change some sort of variable within the design, and the one we decided to change is what's called an aspect ratio. So an aspect ratio is the wing's span over top of the wing's chord length. So the length basically over the width. And by changing that, you get various different effects over the density, the velocity, and the lift and drag coefficients over top of the foils. So for us, we decided to make two different aspect ratios and see how they stacked up to theoretical applications. In theory, if you have a wing with a higher aspect ratio, it is going to experience less drag and slightly higher lift than a wing with a high aspect ratio. So to show you, a high aspect ratio would be one like this, where it's narrower, skinnier, and longer. And then one like this, where it's a little bit fatter, is going to be a lower aspect ratio.
Yep, so now that we understand the background of our experiment, it's time to get into our methodology or our path that we followed. So obviously the first phase was design. So with that phase, it was more or less based around designing and manufacturing our parts. So we used 3D modeling in CAD, as well as 3D printing with plastic filament, which brought us into our testing phase. So obviously that phase consisted of mounting everything, rigging up the static pressure tubes into our machine here, and then running trials and collecting data. And then lastly, once we received our data, we used that to graph it against the other variables in order to find trends that would display relationships between our variables. So first step of the design phase was determining how we wanted to build an accurate airfoil. So we were able to find a resource online that was a database that had thousands of different airfoil designs. And the one that we decided to choose was a NACA 4412, which basically these digits stand for different basically components of the airfoil. So the first digit stands for what percent the thickness is compared to the chord length. And then the second digit correlates to how far along the chord length is the thickest component. So once we determined which one we wanted to use, we were able to import it into CAD. And basically, this allowed us to display that the aspect ratio is represented, like Matthew said, the span over the chord length. And then once we modeled the airfoils, we also implemented an access panel on the bottom side of our airfoils that we could use to put our static pressure taps through, as well as a stagnation tap through the front. And then our plan was to have a 90-degree angle within this access panel, because we basically have a pocket in here that we could use some soft tubing to create a 90-degree angle and then have that come out the bottom. Unfortunately, once we built this, drilled our hole through and put brass tubing through, we realized that we more or less pinned our access panel into place and were no longer able to remove it. So that was an oversight we had and a lesson that we learned. But moving on, like I said, the 3D printing, one flaw that we occurred while doing it was the base of our 3D printer was only 10 inches by 10 inches by 10 inches high. So we ended up having to print our 12-inch span wings at a hypotenuse 45-degree angle on the bed using supports. So while printing, we incurred 2 failed prints, which set us back and was very frustrating. However, we were able to get finished components, but the surface finish wasn't exactly perfectly smooth. There were slight abrasions or weak spots. So what we ended up doing, as shown by the picture, is using sandpaper to get it as smooth as we possibly could, and we were able to make it work. And then this picture is basically to display or show the access panels on the bottoms of both airfoils. Although they are the exact same dimensions in terms of length and width, we did have to design 2 separate access panels for both due to the change in thickness. Because if we were to use the same access panel from the smaller aspect ratio on the larger aspect ratio, we would have had more parts sticking out and created a second stagnation point along our air draft. So lastly, last phase of our design component was drilling out and putting in the static pressure taps, which I previously mentioned, and then hooking them up in the wind tunnel. So now that we finished with design phase, moving on to the testing phase, here we have our procedure laid out. It's fairly simple, basically consisted of mounting our airfoil in the wind tunnel, connecting the static pressure taps, and then once we got everything set up, we were able to turn on the wind tunnel, turn on and set the fan frequency, and basically let everything stabilize before we started collecting data to make sure that everything was running smoothly. So the components that we measured manually were temperature, drag, lift, and the wind tunnel manometer reading from the pitot tube. And then we also had the computer automatically calculate and measure the static pressure tap pressure points for us before moving on to a new frequency. So going through our testing phase here, first step was obviously getting it set up and calibrating the lift and drag rig. So we did that by using zip ties as well as a pulley system and a hanging mass. Ray and I went through, the hanging mass is 1.4 pounds, and we incrementally added 1 pound plates to make sure that as the amount of force we added, the system was staying consistent. So our drag units ended up being very precise, and we didn't have any issues, but we found that with the lift measurements, the more weight we added, the more variance the machine readings gave us. Luckily, the frequencies that we chose to test at were very low, so we basically chose to neglect the variance in our lift measurement due to it being very insignificant. So, like I mentioned, this machine was able to calculate the static pressure tap measurements for us, and although it has 40 some odd points for you to hook in tubes, we only used 2 pressure taps per airfoil, one closer to the front of the top of the surface and then one near the back to see if pressure would change as air flew across the top of the surface, if you want to get a close-up view of that. So we use data points 13 and 14, and this manometer back here, since we had an issue with getting the stagnation point from our airfoil, we used the stagnation point from the pitot tube to basically use that as a replacement and solve for velocity that way. And then lastly, we, after each trial was said and done, we made sure that the angle remained constant before adjusting to a new speed. Mm-hmm. And once we got all our measurements done, I wanted to see if our airfoils would be able to withstand the maximum fan speed. So I cranked it up to 58 hertz, and it was able to withstand it. Actually, the airfoil with the higher aspect ratio was able to, but the airfoil with the lower aspect ratio, once I cranked it up, basically shot down. And that was due to a flaw with our mount design. We didn't have the holes perfectly lined up, so we more or less had a bolt ran through plastic and just clamping it against the metal plate in there.
So once getting the tested raw data, it was important for us to understand what values we needed to find and what path would be necessary to calculate those in order to draw conclusions about the applications of changing that aspect ratio on the other variables. So the main ones that we needed to find were the air density over top of the foil, the air velocity over top of the foil, and the coefficients of drag and lift over the top of each foil. Now the path to do this was first convert all of our raw data measurements that we got from the manometer as well as the digital manometer from inches of H2O into more applicable units, so PSIG for us. And then next was to calculate the absolute stagnation pressure, which is necessary to find the air density in the ideal gas law equation. Next, we had to utilize Bernoulli's principle in order to find the air velocity going over top of each of the foils. Next, find the coefficient of drag and lift using the equations from class to find with the air density that we calculated previously. And last, by generating graphical representations of these, we'd be able to draw conclusions from our data. So here is the massive raw data tables. Now I know it seems like a bit much, but I'll point out the key items here. So this is for the smaller aspect ratio foil, so the shorter and thicker one. And then here is for the higher aspect ratio foil, which is the narrower long one. And now the key variables here to point out are we got the drag and lift for each airfoil in pounds force, as well as we got the static, stagnation, and pressure drop from each of these foils as well. Now here was the fluid fundamental paths that we used with this raw data to understand and calculate the variables we needed. So first we used Bernoulli's principle between the stagnation point from the pitot tube and the static pressure point on the utmost rear of each of the foils to find our velocity of the air. Then we used the ideal gas equation in order to find the density of the air over the foils. Now here was the calculated velocity and density data. Again, large tables, but to point out, for the smaller aspect ratio foil, we were able to calculate the density at each of our trials and the velocity, as well as for the higher aspect ratio foil, we calculated the density and velocity for each trial. Now, the fluid fundamental path to understand the coefficient of drag and lift was using the equations that we had from class. And here is the calculated data from those tables. Now, for each aspect ratio, for each foil, we were able to find coefficient of drag and coefficient of lift. And something I want to point out that's important here is to find that frontal area, we actually used an equation from the chord length from the background info, which was span squared over the area equals the aspect ratio. So we utilized the span length and the aspect ratio of each to find our necessary frontal area. Now this is where we start to get into the meat and potatoes, where we can actually draw conclusions from our calculated data. So this first figure here shows the fan speed of each of our trials, as well as the velocity on the y-axis of the air going over the foil. And you'll notice we have two lines here. And for a point of reference, each graph moving forward The blue line is the smaller aspect ratio wing, and the red line is the higher aspect ratio wing. What this is showing is that as the fan speed increased between trials, for both foils, the velocity increased almost directly proportionally, meaning that as we increase the fan speed, the velocity is going to increase by a similar metric. What this allows us to do is to plot each of our other key variables over the fan speed, and then we can make conclusions about how that changes with velocity as well. So here, figures 2 and 3, we can get some real-world applications of these foils. First, on figure 2, we have the fan speed graphed against the lift force for each of the foils, as well as figure 3, we have the fan speed graphed against the drag force for each of the foils. Now, for figure 2, this is actually inconsistent with what theoretical aeronautics would tell us. This is showing that the airfoil with the lower aspect ratio has less lift force compared to that of the higher aspect ratio. Typically, in theory, we would believe that the higher aspect ratio wing would have higher lift forces, and the reason we believe this is slightly inconsistent with theory is due to the 3D printing making a rough surface finish, as well as the lift drag unit in the wind tunnel is typically designed for much longer foils, therefore is unable to get as accurate of a reading as we want with our smaller foils. Figure 3, however, is very accurate with what theory would tell us, as it shows that the foil with the higher aspect ratio consistently has a lower drag force magnitude than that of the foil with the lower aspect ratio. This is what we would expect from a foil with a high aspect ratio, as you get longer and skinnier, the wingtips are going to be farther from the base of the wing, meaning they are going to produce less drag force. Figures 5 and 6 here are the fan speed for each foil versus the coefficient of lift, and the fan speed for each foil versus the coefficient of drag. Now here, again, this is similar to figure 3 that we showed previously, figure 2, which displayed that the coefficient or the lift forces were inconsistent, and again, that can be contributed due to the rough surface finish. However, figure 6 allows us to draw real implications for what type of aspect ratio we would want in a real-world application. As we can see, the lower aspect ratio foil at low speeds has a much lower coefficient of drag. However, as we get to steadier high velocities, the foil with the higher aspect ratio decreases to a point where it has then a lower coefficient of drag compared to the fat foil. Now, the conclusion we can draw from this is a lower aspect ratio foil would be more applicable at a low speed for short burst maneuverability, where a high aspect ratio foil would be more applicable for a constant high velocity application. Because as we can see, as the coefficient of drag decreased, the fan speed increased.
And a lot of air shows where they have those stunt planes that are very good at maneuverability use airfoils with a low aspect ratio because they are better at low speeds, being able to do all the stunts and tricks and such.
And then lastly, figures 7 and 8 display both of our foils with the air density compared to the lift force and the air density compared to the drag force. Now I want to point out figure 8 in specific here, as again, we can draw a real-world application for each of these foils. We can see that consistently the foil with the higher aspect ratio has a lower magnitude drag force than that of the lower aspect ratio. Now, what we can conclude from this is that if we have a lower air density, we are going to consistently have a lower drag force acting on a high aspect ratio wing. Meaning, at a high altitude, we would want to be using a high aspect ratio wing when compared to a low aspect ratio wing. So I previously stated them, but I want to highlight the 3 main takeaways from real-world application from our testing. 1, a higher aspect ratio wing is more applicable to high altitude flight or a actual aircraft. And like I said, that is because as the density decreased of the air around it, it still consistently had less drag force, therefore would perform better at a high altitude. Also, higher aspect ratio wings are more applicable for high velocity, longer duration flight, as well as would be better for mitigating emissions from a aircraft. And the reason for that is because it consistently had a lower coefficient of drag and lower drag forces, it would then require less power from the motor of the aircraft in order to overcome those drag forces and mitigate emissions. Lastly, as Adam stated, the lower aspect ratio wings are more appropriate for maneuverability, as we see with airplanes from air shows, as at lower airspeeds, they were able to perform better with the coefficient of drag.
So now we're going to talk about the lessons that we learned from our experiment and what we would recommend to those doing this or copying this experiment in the future. So obviously we learned how the fluid mechanics apply and impact the results of aeronautical applications and guide the decision-making process when it comes to choosing which aspect ratio you want to use for certain applications. And we now that we understand the relationship between the variables that have an impact on aspect ratio and lift and drag, we can dictate how the style of airfoil is chosen. In the future, we would recommend using either a different manufacturing technique or a different printer style when making these. Talking with Ray Rust, we basically decided that in the future we would either use a printer with a larger bed that would allow the part to be manufactured flat, that would leave a better surface finish without having to rely on supports to hold it up. It would also lead to less failures. Or another option we discussed was using metal and having these laser cut for the smoothest finish possible and most accurate, but due to time constraints, we didn't decide to pursue that option. Additionally, we would try to gather more information and more trials from the lab, so that way we could have more concrete evidence in our trends and basically have more concrete conclusions.
And so a key question here is, why does this matter in the real world for applications on aircraft? And as we have both worked in engineering industry for the past 2.5 years at Kettering, we know it is an engineer's moral responsibility to continue to innovate in their field towards a sustainable tomorrow. As we discussed, we found the optimal airfoil for different applications of an airplane, and if they were the most optimized airfoil, that means they would be using the least amount of power from the aircraft engine if they had the optimized airfoil, therefore emitting the least amount of emissions possible. So overall, this helped us recognize the importance of optimizing an airfoil for different applications in order to not only reduce drag, but also reduce power and emissions needed from an airplane with the certain airfoils.
So lastly, would we recommend this project for students in the future? After going through this, we would say that this played an integral role in our fluid mechanics understanding and path this term, especially with lift and drag. We kind of covered it towards the end of the course, and more so the information that we covered in class was a general overview because the calculations that come are more or less plugging and chugging variables. So we believe this project, as we got into the weeds, there's a lot more to consider than we initially thought when we went over it in class. So we would strongly recommend this project for that reason moving forward. Not even just aeronautical applications, but I mean all the projects that we've seen here today, many students got way deeper than we have in class, and we believe that one of the key factors that contributed to our success was checking in with Dr. Berry weekly and making sure that we were having constant progress as opposed to just trying to as opposed to trying to cram everything at the end and just throwing together a presentation. We actually understand what we were presenting, and because of that, make for a more thorough presentation.
I agree.
Yeah, meeting week to week and actually working on something we're interested in allowed us to further our knowledge path, as well as continue to practice the fundamentals such as lift and drag forces, as well as Bernoulli's principle. So we strongly recommend this project moving forward.
Okay.
Any questions?
All right, guys. One thing, I admit that you learn much more than I could have talked about in the classroom, about the trade-off issues between high aspect ratio, low aspect ratio, influence about high altitude, low altitude. So just from that aspect alone, I mean, they have learned so much more than anybody could have taught them actually in the classroom, just talking about the news principles. So good job, excellent job.
Thank you.